So in the previous lecture, we discussed how we can use the determinant of Hessian method to detect the blobs in images. In this lecture, we will see how we can use the determinant of Hessian not as a primary blob detector but as an eliminator of the weak blob responses or false blob responses in the log or difference of Gaussians based pipelines. Furthermore, the determinant of Hessian is actually used as a filtering method in the SIFT algorithm. And before going to how we can use this as an eliminator of the weak or false responses, we will first summarize whatever we have learned in the previous lecture when the determinant of Hessian was used to identify or detect blobs in images. So we have an input image I. We construct the Gaussian scale space of the image I parameterized by sigma. And the next step is to compute the Hessian of the Gaussian response of the image functions at every scale, where the scale is denoted by sigma, where sigma is the standard deviation of the underlying Gaussian function. So in the previous lecture, we studied that the Hessian can be broken into individual components. So it's going to be a 2x2 matrix at every pixel coordinate p, and can be broken into its individual components. So its components are second order partial derivative of the Gaussian function convolved with the image. Using the ideas from the Laplacian of Gaussian lecture, the Laplacian of Gaussian is same as first convolving the image function with Gaussian and then taking its Laplacian, or we can just compute a Laplacian of Gaussian filter and convolve it with the image. So the same thing, same idea we apply over here. So we compute the Gaussian derivative, second order Gaussian derivative with respect to x, second order Gaussian derivative with respect to x and y, and the second order partial derivative of Gaussian with respect to y, and we convolve the image function with the respective functions. And we can represent these individual components as three different matrices: A sigma, C sigma, and B sigma. And the subscript sigma again here denotes our dependence of the Hessian on the scale. So as we discussed previously, we can efficiently pre-compute these matrices and store them. So each of these matrices are going to be the same as the image dimension, and to compute the Hessian at any given coordinate p, we can just query the matrices at point p. So the Hessian at pixel coordinate p is same as A sigma p, C sigma p, C sigma p, and B sigma p. Furthermore, the determinant of Hessian is computed as A sigma times B sigma minus C sigma square, where A sigma is denoted by the del xx, B sigma is del xy, del yy, and C sigma as del xy. Furthermore, recall that we discussed that instead of dealing with the determinant of Hessian, we compute the scale normalized determinant of Hessian score, which is the multiplication of the determinant of Hessian with sigma to the power 4. And we can compute the eigenvalues of this Hessian, and if both the eigenvalues are greater than some threshold and are greater than 0, then this denotes a blob. Thus the curvature is large in all the directions and also in the two principal directions pointed at by the eigenvectors corresponding to these eigenvalues. Similarly, recall we stated that if both the eigenvalues are close to 0, then it indicates a 0 curvature in all the principal directions, and thus this is a planar surface. So this is our case number 1, this is our case number 2, and when one eigenvalue is larger than 0 and also threshold, and the second eigenvalue is close to 0, then this indicates a cylindrical region or an edge in the image function. So which is this point over here. And recall that we studied that if both the eigenvalues are large, but one of the eigenvalues is significantly larger than the other eigenvalue, then the curvature is large in the first principal direction and is significantly larger than the curvature in the second principal direction, which we can understand from this point 4 over here. Furthermore, recall that we studied that the product of the eigenvalues of the Hessian of the Gaussian convoluted image function is also known as the Gaussian curvature, and the Gaussian curvature is equal to the determinant of Hessian. So we can see that when the product of these eigenvalues is large, that is when the Gaussian curvature is large, or when the determinant of Hessian is large, it indicates the presence of a blob at that pixel coordinate. And thus, by using the determinant of Hessian or the scale normalized determinant of Hessian as a score function, we can detect blobs in images. So this idea is further extended to be used as a filter to filter out the weak responses or the false positive responses in the typical blob detection pipelines based on the log or the difference of Gaussian detectors. So as you can see, by analyzing the eigenvalues, when the product of eigenvalues is large, they indicate blob, and when the product of eigenvalues is small, they indicate either a planar region or an edge in the image function, in the Gaussian convoluted image function at that particular scale, sigma. So now we will extend this idea further to be used as an eliminator of the weak or the false positive responses in the typical blob detection pipelines. And this criteria was introduced in the SIFT paper and is part of the SIFT algorithm. So the determinant of Hessian is used as a filter in the SIFT algorithm, which we'll see what it is. So as we studied earlier, that along the edges there is large curvature in one principal direction, but in the other principal direction the curvature is very small or close to 0. Furthermore, the eigenvalues of H sigma, that is the lambda 1 and lambda 2, are also proportional to the principal curvatures of the difference of Gaussian response of the image function at that particular pixel coordinate where we are computing these eigenvalues, and at that particular scale as parameterized by the parameter sigma. So at any given pixel coordinate p and at any given scale sigma, the eigenvalues of the Hessian of the Gaussian response of the image function, so these eigenvalues are proportional to the principal curvatures of the difference of Gaussian response of the image function. So as we discussed earlier as well, that typically when we are using it as an eliminator, we typically use it in the blob detection pipelines that are based on log or the difference of Gaussian detectors. So these eigenvalues are proportional to the principal curvatures of the dog response of the image function. So we can simply analyze the eigenvalues of this Hessian matrix to determine if a particular candidate pixel coordinate P indicates a blob or an edge in an image. So we can do this by simply checking the ratio of the eigenvalues. So if this ratio is close to 1, so for example, if the eigenvalue lambda 1 is significantly some n number of times larger than lambda 2, then relative to the curvature in the first principal direction, the curvature in the second principal direction is very, very weak. And this point thus indicates the presence of an edge rather than a blob in an image. So if lambda 1 is significantly large, then this point represents an edge rather than a blob. And if the blob is circular, then both the eigenvalues will be very close to each other, and they both will be greater than 0 or some threshold tau as well. Furthermore, if the blob is ellipsoidal, then the lambda 1 would be significantly greater than lambda 2, but not by a huge factor. So if the lambda 1 is larger than lambda 2, then this indicates perhaps an ellipsoidal blob in the image. But if this is significantly large, like maybe lambda 1 is equal to 100 times lambda 2, it means that the feature roughly looks like this in an image, which can be classified as an edge as well. So if the ratio is close to 1, then this is an ideal circular blob, and the ratio is large but not too large. So if the ratio is large enough but not too large, maybe on some threshold, so we can set some threshold like 10 or 20 or whatever number we select as a threshold. So if the ratio is less than this threshold, then we can still consider these points as blobs. But if the ratio exceeds this threshold, we can call it as tau 1. If the ratio exceeds this threshold, then we remove that point as a candidate blob point, and this point is filtered out. And the reason for doing all this is because the difference of Gaussian, as we studied earlier, it approximates the scale normalized log function, and the log function is used for both the edge and blob detection. So the log response for edge and blob is high, and thus the dog response is also going to be high for the blob and edges, and thus we need to have a method to filter out those false positive or weak responses using the determinant of Hessian. So the question is, how do we compute this ratio of eigenvalues without explicitly computing these eigenvalues? So computing these eigenvalues explicitly may be computationally very expensive, and thus we need to have a better function that approximates this ratio without requiring us to explicitly compute it. So this is what is proposed in SIFT paper. So without the loss of generality, we can assume that lambda 1 is greater than lambda 2. And now from the basic mathematics, we know that the trace of the Hessian is equal to the summation of the eigenvalues, and the determinant of Hessian is equal to the product of eigenvalues. And here, when we are dealing with ratio, when we are using the determinant of Hessian to filter out the points, we don't have to scale normalize it. So we don't have to multiply it by the sigma to the power 4. So the determinant of Hessian at any given pixel coordinate p can be just computed as a sigma p times b sigma p minus c sigma p squared. And the trace of this Hessian is just a sigma p plus b sigma p. So in an unlikely event, when lambda 1 and lambda 2 have opposite signs, in that case we discard the pixel coordinate p as candidate blob. So we discard it as candidate blob point. So if the determinant of Hessian is negative, then the pixel coordinate p is discarded as a candidate blob point. Now we can represent the ratio lambda 1 over lambda 2 as gamma. Now we can compute our function f of h sigma as trace of H sigma square over determinant of H sigma, which is equal to lambda 1 plus lambda 2 squared over lambda 1 times lambda 2, which is gamma times lambda 2, so gamma plus 1 squared lambda 2 squared over gamma lambda 2 squared. So the gamma cancels out and we are left with FH sigma is equal to gamma plus 1 square over gamma. So this function grows as gamma increases. So as gamma increases, FH sigma also increases. Thus, we can use this function as a proxy for gamma. So to compute this function, we just have to compute the ratio of the trace of the Hessian squared over determinant of Hessian. And this is much more efficient than computing the eigenvalues of the Hessian. So we can use this function as a proxy for the ratio of the eigenvalues gamma. In SIFT paper, the threshold for the value of gamma was 10. That is, any point where gamma is less than 10 was kept as a blob point in the final dog response of the images, and any point where the ratio or the gamma exceeded 10, those points were deleted as candidate blob points. Which means that the function FH sigma should be less than equal to 11 square over 10, which is 12.1. And as shown in the SIFT paper, using this elimination method for eliminating the weak responses or false positive responses significantly improved the quality of detected blobs. And this is how the Hessian method or the determinant of Hessian method was used to eliminate the false positive points in the SIFT algorithm. And we can use it in any of the blob detection pipelines that are based on either the log response or the difference of Gaussian response or image. Furthermore, as we discussed previously, we run this elimination process once we compute the local maxima after doing a 3D or the 4D non-maximal suppression. So depending on how you implement, if you are using octaves, as we discussed in the lecture for octaves, if we are using octaves as opposed to using just the Gaussian scale space, then the final implementation for the final non-maximal suppression will be performed in X, Y sigma and the octave space, and depending on how you implement it, this can either be turned into a 3D search where we search along X, Y and sigma and octave combined, or if we have a naive implementation, then we can convert it into a 4D search, searching in X, Y, sigma and then finally in octaves. So the leftover blob points after this 3D or 4D search, it can be 4D only when we are using octaves. So after performing this 3D or 4D search for the local extremums, the leftover local extremums were finally classified as blob points in our log and dog based blob algorithms, and we can then further run the determinant of Hessian based elimination method on the survived local extremums, and any point where the value of this function is larger than 12.1, we can discard those points as blob points, and anywhere where this value is low, we can keep those extremums as the final blobs in our images. So this concludes our discussion of using the determinant of Hessian as a method for eliminating the false positive blob responses. And this also ends our discussion of the determinant of Hessian, where in previous lecture we discussed how we can use the determinant of Hessian, the scale normalized determinant of Hessian, to compute blobs and images. And in this lecture we discussed how we can use the determinant of Hessian method to eliminate the false positive responses. This also concludes our discussion of blobs and in general the discussion of features in images.